the last notes of this unit. To get through 142 through 144, I'm actually not going to do all of these problems for you, but I am going to set up them so you can kind of get an idea of what's going on. So if you're stuck on setting them up, this is a good one to watch. So 142 through 144 of your daily lessons. On 142, okay, the first one, a box is to be built from a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long. So first thing I'm going to do is I'm going to draw that. So this side is 40 centimeters and by 25 centimeters. And then you cut out a square from each corner. So what happens when you cut out a square is that you can actually start folding up the edges. A square, though, has the same length and same width. And you're not going to cut out different size squares from each corner. And it says cut out a square from each corner and then bending up the sides. So what happens is you cut it out and you bend up the sides and you make a box. And this one, and it's going to be an open top. Find the size of the corner square that will produce the container that will hold the most amount of soup. Okay, this is where I don't think that you would take a cardboard box, cut out a side, and then, fold it up to contain soup, because I feel like the soup's going to drip out. But, it's up to you. So maybe if you need a soup container, you can cut out a piece of cardboard and do this. So if you don't know what you're talking about right now as far as like cutting out sides, stop this and actually have somebody at your table do it. Like cut out a square from each side that's the same size, fold it up, you can see how it makes a box. So you can stop me, you can do that now. This one says that will produce the container that will hold the most amount of soup. If you're thinking about an amount of something, an amount of liquid, you should be thinking, I want to optimize volume. Okay, and optimizing volume. You can have volume as length times width times height. Even for a box, even if it doesn't have a lid. But the way that we're going to do this is I'm going to say volume, and I'm going to think about what each of these sides are. And I'm just going to say, I'm going to cut out all these sides with x. So all these things are here, x, 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 x. So volume, if I'm optimizing volume, what I'm doing is I'm going to take the length. Let's say 40. That's what I started with. But remember, I cut out something that's x sizes on this side and x on this side. So I'm taking 40, but I'm taking 2 x's away from it on my length. So it was 40, now I'm taking this one away and taking this one away, so minus 2x. Then, my width, I did have 25, but again, I'm taking an x way here and an x way here. So I get 25 minus 2x. Length times width times height. When I fold up the box, it's going to be as big as this square is, or at least the height of the square, so I'm going to say times x. If you are optimizing anything, you need to take the derivative. Take the time, actually multiply this out, do that now. You should get that volume is equal to 4x cubed minus 130x squared plus 1000x. What you're going to do then is take the derivative. So you get 12x squared minus 260x. Set this equal to 0 and see what happens. When is this thing 0 equal to this? Do that now. Pause the video so you can do it. You will get two answers. X is equal to 50 over 3 and x is equal to 5. So 50 over 3 and 5. What you need to see is when is there a max, when is there a min? Are both of these maxes or both of them mins? You need to figure that out. If you make a chart, x and b prime, because I want to know is the volume, not velocity, is volume increasing or decreasing, so is the derivative of volume positive or negative. If I go from 0 to 5, and then 5, and 5 to 50 over 3, 50 over 3, 50 over 3 to infinity. Here I get 0, 0. I can see that this value, if I plug this back into b prime, this will be positive, negative, positive. Which means there's a minimum amount of soup, so sad. Over here 50 over 3, and a maximum at 5. So, my answer in this one, it says find the size of the corner square. So right now I know x is going to be equal to 5, but it's asking for the size of the corner square, so you have to make sure that you find that. X is equal to a length, so I've got 5 centimeters by 5 centimeters. I said I wasn't going to do this, and then I ended up doing the whole problem anyway. You know, maybe in the next one. Okay, a rectangular page is to contain 24 square inches of print. Okay, so when you're thinking about when you're printing something out, it has margins on it. So think about 24 square inches of print in the inside. The margins at the top and the bottom of the page are to be 1.5 inches, and the left and the right are to be 1 inch. So, get a piece of paper, and in here, you got some margins. And it's saying that up at the top, it's 1.5 inches, and the bottom is 1.5 inches. Inches. And then the sides, the left and the right, it's 1 inch and 1 inch. It's saying, what should the dimensions of the page be so that the least amount of paper is used? So what I'm doing is I'm still optimizing, I'm just minimizing on this one. I'm trying to find the minimum amount of paper. Amount of paper is going to be area. So you have to think about the area, but it's of the entire piece of paper. So the area of the big piece of paper, which I can think about is just length and the width. Length times the width. I don't want to take the derivative of that. I want to make this easier. So I have to think about, okay, well, what exactly does this look like? So the way that I do that is I can actually figure out, I know that the rectangular pages contain 24 square inches of print. So the area of the print, then, I know is this. So I have L to begin with, but I'm going to take L and subtract the 1 inch here and the 1 inch here, because it's on both sides, so L minus 2. On the other side, I'm going to take W and subtract 1.5 and 1.5, so W minus 3. And I know that the area of the print is actually 24. It doesn't matter if you solve for L or if you solve for W. I solved for W. So, you know, if you want to be cool like me, you can be. So I took 24, I divided both sides by L minus 2. So I get 24 over L minus 2 is equal to W minus 2. So if you add 2, you can do that all in one step, so you just get that is equal to W. Except, I don't know why I did this, but do you see how this 3 turned into a 2? That's silly. So what I'm going to do is actually write the correct thing. So plus 3 is equal to W. Whew, much better. If you were nervous, don't worry, we made it through that. Okay, so 24 over the quantity L minus 2 plus 3 is equal to W. So I'm going to go back over here. I have L. And I have 24 over the quantity L minus 2 plus 3. And if you want, you can take the derivative right now. I don't want to. I want to actually distribute this first. I want to say 24L over L minus 2 plus 3L. You're starting to notice that here I still have a quotient. Yes, but you know, you can do it. I'm going to tell you that I did the quotient over on the side and check it. So right now, do the quotient rule. Bottom times derivative top minus top derivative bottom over the bottom squared. A prime. You should get, after you simplify all of that mess, that this derivative is negative 48 over L minus 2 squared plus 3. If you didn't get that, stop this, go back, figure out what your mistake is. The next thing that you're going to do is you're going to set this equal to 0. That whole thing equal to 0. So A prime of the big one. So set it equal to 0, see what you get. In a second you should get L is equal to 6 and L is equal to negative 2. This one doesn't make sense. So I've got length is equal to 6. In this one it says least amount of paper and it doesn't really give us any other options. if you want to take the derivative and if you want to make a chart. I'm running out of room on this one, so I'm not going to. This actually is a minimum, but I need to make sure I answer the question. It says, what should the dimensions of the page be so the least amount of paper is used? So I need the length and the width. I know the length is 6. 6 what? 6 inches. So length equals 6 inches. Width. I can use, where is it? Here it is, 24 over L minus 2. So 24 over 6 minus 2. 6 minus 2 is 4. 24 divided by 4 is 6. Plus 3. Ta-da! We did it! Okay, if you need a second, again, I'm going to move on, but it's a video, so you can stop it. Okay, a rectangle is bounded by the x and y axis. Whew, these are good ones. Okay. What is the length and the width should be so the rectangle, so that its area is the maximum. So area of a rectangle is just length times width. But if we're talking about on a coordinate grid, and I'm starting at 0, this distance is going to be the same as x. This distance is going to be the same as y. So I'm going to call this, instead of length times width, I'm going to say x times y. And I want to find when is that area at a maximum. So in this one, I can't just take the derivative yet, because I wouldn't really be able to do anything with it. But I know that y is equal to 3 minus 1/2 x, because it's bounded by that. So area is equal to x. Area is equal to 3x minus 1/2 x squared. So now I can take the derivative pretty easily. A prime 2 times 1/2 is 1. I can set this equal to 0. Okay, x is equal to, oh sorry, this should be negative. So x is equal to 3. So x is equal to 3, but I want to make sure that I answer the question. And by the way, if you do this, you can see it's the only value on here. But if you plug this in and you go